So the title is Exponential Function Context and Data Modeling. It says sometimes data from an exponential function does not display a proportional growth pattern. We're going to see that in these tables right here in just a minute. The way that you have been checking to see if there's an exponential growth is you've been trying to find a common ratio, something that the output values are being multiplied by each time. And if you look at like this first table right here, that doesn't hold true. If you're told this is exponential, well, how can that be? Because we're not multiplying 7 by something specific to get to 13, and 13 by that same number to get to 25. So how is that exponential? So up here where it says, however, if we can add or subtract a constant from the output values to reveal that proportional growth pattern, if I can add or subtract a number from all of these y values, and then that pattern of multiplication shows up, then the initial function was exponential. So we're going to practice that now. Some of you are going to think this is pretty easy, and some of you it's going to blow your mind. So selected values from several exponential functions are given. So first things first, they are telling you right away that we are dealing with an exponential function. For each of these, find the constant that can be added or subtracted to the output values to reveal the proportional growth pattern. And then I'll show you what to do from there. It says, then write an equation to model the function. We'll do that work below the table in that blank space there. Yes. That is not a coincidence. That is something that we're going to figure out here in just a second. That's really good insight. So what you really need to do here is you're told this is exponential, and you're told the task is to figure out what could I add or subtract from each of these to reveal a pattern that shows some kind of multiplication is taking place. The first one I'm just going to show you. I want you to take f of x, I want you to take those y values, those output values, and I want you to subtract 1 from all of them. And I want you to put those numbers in this column of the table. So you're taking your output values and you're subtracting 1. That would give us 6, 12, 24, 48, 96. Interesting. What's the pattern that shows up in that new set of output values? You're multiplying by 2. So when it says to reveal a proportional growth pattern, that's what we're doing. We're revealing now that if I just take those output values and subtract 1, there is a proportional growth pattern. Everything is doubling. How would you know that? If the teacher had said subtract 1 to reveal the pattern, how would you know that? That's just something you're going to have to practice. You're going to have to play around with the numbers. You have to do enough of these in your homework to kind of start to see that. Yes? What do you mean? Yes. And I think that will happen on example about C down here. So here's what I want to show you, okay? Because then it says write an equation to model the function. So here's what we just discovered. F of x minus 1, we should be able to write an exponential model for f of x minus 1, okay? I'm going to write kind of small. Exponential functions are written as a times b to the x power. A is your initial value, b is the growth, the proportional growth. So a, when you're trying to figure out a, look at what is next to 0 in the table. That's your initial value, that's your starting value. So the starting value of f of x minus 1 is 6. So that's a. 6 times What did we multiply by each time? 2, that's your b value, and then to the x power. That's what makes it exponential. So for this red column, this f of x take away 1, for that particular function, here is the function model. But I really need to write a function model for just plain old f of x, okay? So I'm using this to kind of work backwards to get this function. We'll use a little bit of algebra. What's the only thing I need to do in this equation to get f of x by itself? Add 1 to the other side. So f of x's function model is 6 times 2 to the x power plus 1. That's our end result. That's the end game. That's what we're trying to do, is write a function model for f of x, the original function, the exponential function that was sitting there typed on the page. And Peyton had mentioned, is it any coincidence that, how did you say it? If you multiply by 2 and subtract 1, that's how you can get these output values? It's not a coincidence, because that's exactly what pattern is getting. So that was really good for you to see that. Let's try this again. Start all the way over. Okay, we are told that this g of x is an exponential function, and we're supposed to write a function model for it. Well, there's no way to do that right now because these are not being increased by a specific ratio. There's no pattern that emerges right now. But I want you to see if you can kind of play with the numbers. Writing in pencil is going to be good, so you can erase if it's wrong. And try to come up with either adding or subtracting a number. And I'll go ahead and give you a hint. This is going to be adding this time. Adding a value to all of these that will then create a pattern. So just kind of look at that and play with it on your page, because you're going to have to just jump in and figure this out. Like, what can I do to the output values? And my hint to you is we're adding a constant. See if adding 1 makes a pattern emerge. That would be 3, 11, 35. No, that's not good. Try adding 2. 4, 12, 36. Are we on to something? Okay. So add 2 to all of the output values. And sure enough, that's what we needed to find out what is the proportional growth. Yeah, we're multiplying by 3. So what we're going to do down there to get back to the g of x is we're going to start with what we know. We know that g of x plus 2, what's the initial value of this orange values? What's the value of a? 4. It's what's next to 0 in the table, so 0, 4. That would be your starting value. So 4. And then the proportional growth was 3. That's your value of b to the x power. So by one little tiny algebra step, I can get g of x by itself, and that's going to be subtracting 2. Subtract 2. Okay. Look at C. I want you to see if you can figure out, this time I'm not going to tell you if it's add or subtract. I want you to see if you can figure out what can I add or subtract to those output values so that some kind of proportional growth emerges. And Addison asked a key question. It doesn't necessarily have to be multiplied by a whole number. It could be that things are being cut in half or cut into thirds. It could be multiplied by a fraction. That's still a proportional pattern. Does anybody think that they might have it? add 1. So, okay, if you didn't know that, let's take Jonathan's idea. Let's add 1 to all of those output values. Sure enough, a pattern emerges here. Remember, we're looking for something that we're multiplying by. What are we technically multiplying by? 1/2. So this model is an exponential. I think I got carried away with my little brackets there. But this represents an exponential. Is this a growth or a decay? It's a decay. Times 1/2. Times 1/2. Times 1/2. Those were growths. And that's an Algebra 2 concept when your proportional pattern, your common ratio, is larger than 1. It's an exponential growth. When it's between 0 and 1, it's an exponential decay. We touched on that before Thanksgiving break. Alright, so I'm going to take what I know, that h of x plus 1, the starting value is 64. The common ratio is 1/2, that's the b value, to the x power. And from there, the last steps should be pretty easy for you. We're just going to subtract 1 to get the original function, h of x, its function model. Okay, that was one of the tough things that I needed to cover today. And you'll have really good practice on your assignment. Now, the calculator stuff I'm going to show you is not really that difficult, but I want you to look at example 2. This is kind of similar to something you saw on this most recent test, and we did not do well on that. Just, okay. For 0 to 35th time is between 0 and 30 minutes. The number of fans inside a large sports stadium can be modeled by the exponential function, okay? And here's kind of just the skeleton for an exponential function. F is going to represent the number of fans inside the stadium t minutes after the doors open. There are 47 people in the stadium 2 minutes after the doors open. There are 2,602 fans inside the stadium 20 minutes after the doors open. This should sound familiar. This was kind of something we saw on the test. Use the given data to write 2 equations that can be used to find the values for A and B. So we know 2 things. 47 people are in the stadium 2 minutes after the doors open. So if you kind of think of this as a geometric pattern, the second term is 47. So look what you can do. That's one of the equations right there. 2 minutes after, when t is 2, the number of fans is 47. I'm just using this. That means that I can create another equation. When t is 20 minutes after the doors open, the number of fans is 2,602. Now on the test last time, you had to actually just get those values from a table. It wasn't really even a word problem. It was just out of a table. Okay? Your input and output values. But anyway, it's kind of similar to what you saw. So that's it. On the test, you had to, here's where it fell apart for a lot of you. You had to first of all come up with the equations, and most of you couldn't do that. But then you had to solve one of these for A and substitute it into the other equation to figure out what A and B were. It was on the non-calculator portion of the test. But today I'm going to show you how you can find those values in the calculator if this were to appear on an AP test in the calculator. Basically, we're going to just learn how to run an exponential regression model in the calculator. It's the same exact way you learn to do linear and quadratic regression models, but instead of choosing linear or quadratic, you're literally going to just choose exponential. So I'm not really teaching you anything mind blowing. Here's what I want you to do. let's put this stuff in the calculator essentially for this problem about the fans in the stadium. And we're going to have our calculator solve for A and B for us. So I want you to grab your calculator. I want you to open up a new document, a new lists and spreadsheets document. Title your X column and your Y column, whatever you choose to title them. I'm just going to stick with X and Y because it's efficient, it's fast. We're going to take the word problem and we're going to put that in the form of input-output on the table. So there's a little picture of it there. 2 minutes after the stadium opens, 47 fans are inside. That's an ordered pair. 20 minutes after the stadium opens, there are 2,602 fans. You just need 2 points to come up with your regression line. Kind of cool. It tells us in the word problem that this is exponential. That's how I would know as a student if I'm running my regression to choose the exponential part of that. So the steps are there if you need them, but you're going to hit Menu, Statistics, Stat Calculations, and then you're going to go down to option A, which is exponential regression. You're going to do the same thing on this screen that you did for any other type of regression. You're going to tell your calculator, my X list is called X, my Y list is called Y, or whatever you titled them, and then you can go down to OK. And right here, your calculator has solved for A and B. It tells you the initial value. It tells you their proportional growth. So A and B. So I want you to just go ahead and make a note. A is 30.089 and B is 1.24981. We try to avoid rounding. And we got that right off of the calculator. I could use those values then to create a model that I could plug any value to. I could then ask you, tell me how many fans would be in the stadium after an hour. So you would build your model, and then what would you plug in for time if we said 1 hour? You plug in 60 for T, okay? Let's practice that. Yes. I would, yes, because these are rounded values right here. So I would hit, if it asks you for a specific value, I would hit Control 2 and edit your table setting for that specific value. And it might be something that you'll do. No, it's not. But that is exactly what I would do. Instead of using a rounded format. Okay, so here's another example. The selected values of an exponential function are shown. This was more like what you saw on the test, but on the test, the difference was you could do that in binary. A and B were not crazy decimal values. Okay, we have inputs and outputs here. Use the given data to write 2 equations that could be used to find the values for A and B. So if you are planning on retaking the free response, this is really good practice for you to do that. How can I use these two? Think of them as ordered pairs or input-output values. What would my 2 equations look like? Anybody want to tell me what the first one would be? There's one equation. You would solve one of the equations for, I always choose A, because it's easy to get that. So I would solve one of the equations for A and substitute that in the other equation for A. Do you remember in Algebra 2 how you were solving for x and you didn't know either? And so that's the picture. No, that's okay, because I'm sure other people are thinking the same thing. You don't know two different variables. Where do you even start? So the other equation then would be 3.62 equals a times b to the 8th power. That's all they asked for A on part A. Part B, you can use a calculator on this one, so you don't have to use the substitution thing. So run an exponential. I'm just going to start all the way over. Run an exponential regression. I'm just kind of noticing, as an AP student, think about what you're doing. Do you think this is going to be an exponential growth or decay because the y values are getting smaller? Okay, just think of those things. So I expect to get a b value that's between 0 and 1. Those are my values for A. Any questions on running an exponential regression? Okay. You could then say g of x is 62.8012 times 0.6999 to the x power. That would be the model that you could then plug into if the next part of the question asks you to find a specific value. But instead of plugging into this rounded version, I would hit Control T and find that value in the table with that calculator answer. Okay. Next week, we have a whole entire lesson on logarithms. This will just kind of gently introduce you to part of that lesson. E is used as the base in exponential functions that model contextual scenarios. So here's the thing. E is like pi. It's a symbol that represents a number. E is 2.718. It's a constant. It's not a variable. Even though it's a letter in the alphabet, it's a constant, okay? And E might show up here and there, and don't let it scare you. Example 4, the number of bacteria in a particular culture can be modeled by this exponential function. E shows up here. E is what we're multiplying each time by. It's like A times B to the x power. It's like your B. T is measured in hours. Always pay attention, like in problems with time. If it tells you in the beginning that T is hours, and then it says, something about 30 minutes, what would you plug in for T? Okay, so just be careful on those. I see that thing show up a lot. Just be careful. So T is in hours. So part A. Let A of T equal A times B to the T be an equivalent expression for B of T. Yes, of course. Find the value of A. All that is saying is, look up here at B of T. What is the initial value? In other words, how many bacteria do we start with? 17. It's actually a very easy question. If you can make it through all the jargon, it just wants A, which is 17. A is the initial value just as a note, A is 17. And that just means that we started with 17 bacteria. And from there, they're growing at a rate of, what's that? It's saying that if this can be modeled as A times B to the power of T, what's A? And so A is just in that first position. B says, oh, we're bringing in some old knowledge here. Find the average rate of change from 1 to 7 hours. That's the interval. So on average, how are these bacteria changing from 1 to 7 hours? So average rate of change, that's like slope. It's your change in your y values over your change in your x values. Well, what that means to us is we're going to find b of 1 minus b of 7 over 1 minus 7. Or you could flip-flop. You could say b of 7 minus b over 7 minus 1. You're going to get the same answer. That's our task. So now, let's plug in 1 to the function. Let's plug in 7 to the function, subtract those, and put it all over negative 6. So 1 minus 7 is negative 6. I made it sound really easy, but the work to show on the paper is going to be a little bit tricky. So I'm plugging in 1 to this function right here, this b of t. So 17 times e to the 0.31 times 1 power minus 17 times e to the 0.31 times 7 power, all divided by, well, 1 minus 7 is negative 6. You can type all of that into your calculator in one fell swoop and get your answer. There's an E button, just like a pi button. So if you're kind of wondering, well, how do I get to the calculator screen? Just hit your little scratch pad button right here, and it'll take you to the calculator. And we've got this big crazy fraction, so let's hit Control Divide. 17, and then E is right here. And it forces it to have an exponential, which is fine because we need that in exponent. So 0.31. Look, I don't really feel like I need to type in 0.31 times 1. So I'm not going to do that. I'm just going to type in 0.31. Now arrow over to hit your subtract button. So always pay attention to what you're doing. So we're going to subtract 17e to the power 0.31 times 7. All over negative 6, and I hope this works. Okay, good. That's what I got the first time. So 20.952. The average rate of change on the interval from 1 to 7 hours is 20.9521. If you were wanting to attach some units to that, because we're talking about slope, change in y or change in x, that would be bacteria per hour. To put it in context. Okay. When I started today, I said that this lesson was kind of tough. This is where some of you are going to get frustrated. This calculator part that's about to happen. You're going to just have to get comfortable with graphing some things in the calculator, finding where the heck they are on the screen, and kind of like zooming in and out and being comfortable with all of that. I know that can be frustrating, but if you can be confident in your skills, then you're going to be just fine. This says to find T when the bacteria is 1,000. So in this formula right up here, this B of T formula, this function model, where do I plug in the 1,000? You're going to plug it in over here, 1,000. The bacteria is 1,000. I'm trying to figure out how many hours that took. So I would need to be solving for T. Now you're going to have to take my word for it. Next week, you might actually have to use algebra to solve for this. Here's the algebra involved. Does that look fun? Natural logs and switching from exponential form to logarithmic form and then getting your answer? No, we're going to avoid that. We're going to go the graphing route, okay? And here's what we're going to do. We're going to find on the graph where the left-hand side of the equation, we're going to put that in like the y1 line, the f1 line, where that and the left-hand side, where it intersects the right-hand side in the calculator. Here's what I need. Open up a graph document. Type in 1,000. Hit enter. Why can't you see anything? If you just graphed a line way up there at 1,000. So we'll zoom and do all of our stuff in just a minute. But that's what you just did. You graphed a horizontal line at y equals 1,000. All right, now hit tab. And I want you to put this thing, this exponential, into F2. So 17 e to the power of 0.31. You can go ahead and put X. Don't put T. I'm going to put X because I'm an X value. I can see part of it there. Is that what you guys want? Okay. I just need to find where this intersects that one line over 1,000. So let's use a little bit of common sense. Hit menu. Go to Windows Zoom. Go to Windows Settings. For now, I'm not going to mess with the X values. I just want to tab down to my Y values. If I know that that horizontal line is way up there at 1,000, I don't really care where I start, but let's go a little bit past that. Let's maybe go to 1,500. And then on your calculator, the Y scale, it'll say, well, what do you need to count by? Honestly, guys, I just always leave that as auto because the calculator can figure that out. So all I did is I changed my Y max to 1,500. I don't know if that's going to work. You're just going to have to play around with it and see. Okay, so now my problem is I see this line. That's the horizontal line. That's all well and good. And I can see the little exponential model kind of hanging out here. I'm just going to drag. So if you will put your cursor somewhere over here and hold down that middle button until you see the hand close, you can actually just drag the graph to the left. I use that feature and click to release it. I use that more than I do the window zooming in and out. Because if I know, dang it, it's just off to the left, I just can almost see it, then I just drag it into the end. Anybody want me to explain that again? Okay, now you should have the skill or to find that intersection, and that's the answer to the problem. Find the intersection. Menu, where do we go from there? Analyze graph, intersection, somewhere to the left, enter, somewhere to the right, enter, right where I want you to draw a picture for yourself. We just found where the exponential and the line at 1,000, we just found where they intersected. They intersect at 13.1, comma, 1,000. Let's look back at the question. Find T when the bacteria is 1,000. So how would I write my answer? 13.1 it's going to be hours, yeah, because T represents time in hours. Yeah. That's a great question. So instead of typing out 1,000, that's just scientific notation. That's 1 times 10 to the third. It's 1 with 3 zeros in it, which is 1,000. Big picture, I mean, that's really not that hard of a thing. Sometimes finding on your screen where they intersect is the toughest part of the whole deal. All right, go to the last page of the notes. Just tie everything together. After 50 deer were introduced to a large wooded area, the population can be modeled by this exponential function, a times b to the t power. T represents years since they were first introduced. T is years. And the population increases by 13% each year. So this is a growth. This is a growth. This is a growth. This is a growth. A. Find A and B and use these values to write an expression for D of T. Okay. D of T. You have everything you need in the word problem. You don't need to run any sort of regression or anything like that. Think about this. A is your starting value. How many deer did we start with? 50. B is what you're multiplying by for every year that goes by. 0.13, there's a problem with that. That would be an exponential decay. That would mean that there's only 13% of the deer that there were last year. There are 100% of the deer from last year and 13% more. So 113% is really what is sitting as the B. So that's just a little extra thing you got to think about. You have seen this sort of problem in like the interest when you invest money and it grows this much each year. You've got to put that 1 point in front. Yes. No, that's a really excellent question. If it said they decreased by 13% each year, what would you put in the parentheses? Never negative. What, 87%? Why? Yes, 87% of the deer remain from the previous year. And those are the problems you see, like a car depreciating in value. If a car depreciates by 13% each year, then the B value is 0.87. So really, really good questions. Okay, and we're missing something really important there. You need the little T or that. So it said find A and B. I'm just going to be lazy and say, well, that's A and that's B. B. According to the model, what's the population of deer after 6 years? That's not tricky at all. We're just finding D of 6, which is 50 times 1.13 to the 6th power. And just plug that in your calculator. 50 1.13 to the power of 6. Don't get too caught up on rounding here. I know that you can't have a partial value of the deer, but let's go ahead and just put 241.34. Deer. Oh, is that not what you got? Oh, I got 104.098. What did I do? Oh. I typed in the wrong thing. Okay, the first time I did it, I got 104.098. Is that what you got? Okay. C. Find T. Find time when the population is expected to reach 5,000. So how many years will it take for the population to reach 5,000? This is like what I showed you on the previous page. Let's graph the left-hand side and the right-hand side and find where they intersect, which is a lot easier than algebraic. Which we'll eventually have to do, but we're trying to just avoid that. Right. So again, big picture, I'm going to find where this exponential growth intersects the horizontal line of y equals 5,000. Just take your time and make sure you're good with that. I don't see anything on my screen, so I'm at least going to change my y values. And as I drag the graph over, I can start to see there we go. I only needed to change my y. I went up to 5,500, and then I just dragged everything over to the left. And now it takes about 37.7 years for the deer population is expected to reach 5,000. Yes. T is in years, so that is years. Yeah, if it said find the number of months, then I would convert it to months. But it just said find T. And T is already up there in the word problem. It says T is already in years. So that's how, in my answer, I'd say about 37.7 years is how I'm at today. We good with that one? Okay. D is interesting. Find an equivalent expression for this word problem where T is measured in months instead of years. Well, we're still starting with 50 deer, and the growth rate is still about 13%. But what we're going to mess with is the exponent. How would you take years? Ooh, this is tricky. How am I going to say this? What do you think you're going to do to the original T value? So we do 12 times years to get months. Now you would do divide by 12. Years divided by 12. Is that right? My brain says 12T. Yeah. Here's how, let's do this. Since we've already answered part B, and we've said after 6 years there would be this many deer, 6 years is how many months? So let's do, we're 72. let's see if this gives us the same answer after 72 months. 72 divided by 12. Okay, this is actually correct. Okay, because my brain was saying, well, if you want to convert years to months, you multiply by 12, so why the heck are we dividing? Well, if I told you 6 years here, T is in months, T is in months. So for 72 months, divide that by 12, and that would be 6 years. So if I'm trying to do like question B, then I would do 6 years, but T is now in months, so that'd be 72 months divided by 12. That's going to be the same thing as to the 6th power, so we would then get the same answer that we got. So I'm justifying to myself that this is correct, because that, for my brain, that hurts. And those I have to kind of justify them. Okay, whew, that was a great way to end. Do you think that